Okay, limits and continuity for our first section of chapter 2. Alright, so first we're going to talk about average and instantaneous speed just to kind of get the idea of where we are going. So just to remember, average speed is distance covered divided by elapsed time, which some of you probably have heard as delta D over delta T, physics people. Alright, so for example, you're going to get things in like meters per second or feet per minute, etc. Miles per hour, and so on. So we're going to talk about velocity, average speed. So a rock breaks loose from the top of a tall cliff. What is the average speed during the first 2 seconds of fall? So we need to know that objects fall at a rate on Earth according to this equation. Okay, we'll get into that a little bit more later. All right, so we're going to write down this equation as delta y over delta t because the change in distance over the change in time. And so our distance at time 2 would be this. Our distance when we initially start would be this. So that'll be our change in distance because this is the distance where we start. This is the distance where we end. So that subtract them, you're going to get your two distances. And then our change in time would be 2 minus 0. You get 32 feet per second if you work that out. And that's the average speed from 0 to 2. But the next is a little bit different. So what if we need to find the speed of the rock at exactly 2 seconds? How do we do that? We don't have the tools right now to do anything but average speed. So we're going to use that concept to do it. So remember, for average speed, we said we needed to have the change in distance over the change in time. Well, what if we said we're starting at time 2, okay, our initial time is at 2 seconds, but then we're going to say our second time is 2 plus a teeny little bit. We're going to call it h. So it might be like 0.1 seconds or maybe 0.01 seconds. All right, so we're going to call it a variable because we're going to change it. We're going to get smaller and smaller. Well, that means my initial position would be 16 times 2 to the second. All right, and my end position then would be 16 times 2 plus h squared, because my time is 2 plus h, and I'm putting it back into that function. Remember, it is defined as 16t to the second objects fall on Earth according to this equation. Now, let's go ahead and plug this in, or substitute it in if you want to be more mathematical in your vocabulary. All right, 2 squared all over. Now we have to do the change in time. So we're going from 2 plus h seconds, 2 seconds to 2 plus h seconds, I should say. So we're going to subtract those. All right, so let's do some algebra. Let's see. When we FOIL that top guy out, we should get 16 times 4 plus 4h plus h squared minus 64 all over. Now on the bottom, I have 2 plus h minus 2, so that's just h. Now you actually have to FOIL to get that top part. I'm going to let you try that, and you should FOIL it out and make sure you agree with me before you move on. All right, so if I'm going to put this here so it's out of our way. If I go ahead and distribute that 16 in front, I should get 64 plus 64h plus 16h squared, and then minus 64. All that is over h. These guys cancel out. All right, now I have 64h plus 16h squared all over h. Well, I noticed that there's an H in both terms on the top. You can't just cancel these H's. You have to cancel everything. So when you are dividing, remember, division is distributive. You're dividing everything by H. So actually, I'm going to think of it as just dividing both terms by H. So I have got 64 divided by H, 64H divided by H, and 16H squared divided by H. So that's just 64 because the H and the H cancel, plus 16, and that H squared divided by H is just going to give me H. So that's what I got there. So that little function, that little equation, tells us the speed of that rock each seconds, milliseconds, whatever we're putting in there, after 2 seconds. All right, so if I want to say, well, what does that look like 1 second after 2 seconds? Okay, so 3 seconds, right? So if I put in H equals 1, if I put in H equals 1, my speed, okay, my average speed on that little interval is going to be 64 plus 16 times 1, which is 80. If I put in something smaller, let's say I only go 0.1 seconds after 2, so I'm at 2.1 seconds now, and I put it into this equation here, I put in 0.1 for H, and I'm going to get that I'm 65.6 is my average speed, feet per second. And what if I say, well, I'll make it even smaller, so I'm even closer to 2 seconds. If I put in H equals 0.01, that means that I'm really only at 2.01 seconds, my average speed from 2 to 2.01 seconds. Well, that average speed turns out to be 64.16. And if I do it even smaller, okay, I'm at 64.016. And you can keep going, but you see we're getting really darn close to 64 feet per second. Turns out that is exactly the speed, not the average speed, but the instantaneous speed at 2 seconds. And we're going to use that idea that we get closer and closer to the actual value if we take smaller and smaller delta t's or time elapsed to be able to tell that. To do that, we're going to use something called a limit. Okay, and so there's this crazy something called a delta epsilon definition, and we're going to talk about that for just a second, but then we're going to talk about what we really use it, like how we actually use it, because the delta epsilon thing is, quite frankly, a little nutty. So it says the definition is assume that f is defined near c, meaning we've got some function and we've got a function and it actually has a value near c. Well, c function, okay? So it actually got a value there. That's a point filled in. All right, now it's defined near c, and you got c being an actual number and L being actual number, and it says the function has a limit as x approaches c. So if I'm getting closer and closer and closer to that c value, okay, it actually has something called a limit. If for any positive number epsilon, it's like a lowercase e in Greek, there's a positive number delta, but it's like a lowercase delta in Greek, so that for every x, we have 0 is less than x minus c is less than delta, implies that f of x minus L, which is the limit, is less than epsilon. So as x is getting really, really small, basically these are approaching each other. So we really say that as x goes to c, it gets really close to L, so we call the limit L, okay? We call that a limit. If we're going along a graph and it's obviously approaching this number, that is what that limit is called. Now, limits does not mean the function equals that. We're going to talk more about that. We say the limit of f of x as x approaches c is L. That's what you say. All right, so now that we introduce that vocabulary, we're going to graph f of x using a calculator and sketch that whole thing. I'm going to actually sketch it out on here. You're going to want to graph it on your calculator. Don't forget that you can use the alpha y1 or y equals, or that's really the F1 key. Okay, if you'd use that, you can actually use the fraction function on there, and you don't have to use all the crazy parentheses that you used to. It makes graphing rational functions, functions that look like fractions, a lot easier. All right, so I drew out my little graph. It looks a lot like a parabola. I know there's a open circle right there, open hole right there, so I put it in. And I want to find the limit as x goes to 1 of f of x. So if I put in 1, what's my value? Well, when I go to this equation and I try to put in 1, I get into trouble because there's a division by 0, and I can't do that. And so I go to my calculator and go, all right, graph, help me out. What's the value at 1? Well, it's an error because there's no value. I can't divide by 0. All right, so what I want to do, the idea of limit is, instead of trying to find the value at 1, find the values close by. So you start kind of big. So I went out, I can't fit my 3 decimal places in, but I'm going to try my best. So at 0.75, I'm at 2.3. At 1.25, so just a quarter out from what I'm looking for, each direction, then I'm at 3.01. 81, excuse me. Then if I say, well, let's get a little closer. Let's only go a tenth away from 1. So at 0.9, which is a tenth away from 1, I'm at 2.71. You can get these from your calculator. Okay, you can either plug in if you really want to, or you can use your calculator, graphing calculator. If you push trace and then push these numbers in, it'll actually give you the values, so you don't have to calculate each one individually. All right, so 3.31 on the other side, 3.31. All right, now what if I only go out 100th? 100th. So 0.01 away either direction. So at 1.01, I'm at 3.03, and the other direction, I'm at 2.97. And then at 1,000th away, I'm at 3.003. And then at the other direction, I'm at 2.99. So what's happening? As x approaches 1 from the left, I'm getting closer and closer to 3. As x approaches 1 from the right, as I'm going this direction, I'm getting closer and closer again to 3. And since both directions I'm getting close to 3, we say our limit equals 3. All right? So that's the value. If that hole were filled in, it were an actual point, it would be at 1,3. Okay? Now it isn't. It's open. It's not a filled in hole, but its value would be, if it were filled in, 3. So let's try another one. All right, so estimate the limit as x goes to 0 of that crazy looking thing here by finding the values of f near 0. So if I put in 0 there, I hope you can look at it and say, I am going to get 0 on the bottom. I can't divide by 0. But we're going to first look at the graph. It looks very similar to a sideways parabola, something like this. There is a hole at 0. I have guesstimated my graph. Do not go by my graph. I just sketched it out. Now, if you do exactly what we did and go from each direction, I have an extra spot in my table, and I'm going to go closer and closer and closer to 0 and use those values as I get closer to estimate what I'm getting close to on my graph. All right, so if I go a tenth away, I'm at 1.998, and on the other direction, I'm at 2.048, and at 1/100th away, I'm at 2.004, and at 1.994, and then I'm at 1.999, and I'm at 2.000. Okay, I think that we can safely say we're getting closer and closer to 2. We're getting closer and closer to 2. The limit then means we're getting close to 2. We actually never hit 2 because there's a hole there. But my value of my function is getting closer to 2. It never equals 2, but from both directions, it's getting closer and closer to 2. That's a limit. What we're getting close to, maybe never touch, maybe do. All right, so what about a piecewise function? I want you to pause and try to graph this yourself just to practice piecewise. All right, so this is what my graph looks like. It's a line everywhere where x does not equal 3, but at x equals 3, it's just -7. So it ends up just being a point since it's only at x equals 3. Okay, so there's my graph. So the limit as f of x goes to 3, if I look on my graph, what am I getting closer and closer and closer to in both directions? From this direction, coming from the left, I'm getting closer and closer and closer to filling in at 1. And from the other direction, coming from the right, I'm getting closer and closer and closer and closer to the point at 1. So the limit, the function is approaching 1. Okay, what it looks like it's getting close to on the graph, that's different from the actual value of the function. The actual value of the function is at that point way down here. The value of the function, and what your equation tells you the value of the function is -7. That's different from the limit. The limit is what the graph is getting close to from both directions, what that line or the curve is approaching. The line and the curve is actually approaching 1. At x equals 3, it's getting close to y equals 1. All right, so there are non-existent limits, and here are the 3 rules for non-existent limits. First, limits must agree from the left and the right. If they're not going to the same thing, if I'm going up my curve from the left and it's one answer, and I'm going down from the right and it's coming to a different value from the right, then the limit does not exist because it doesn't agree coming from both directions. It has to agree both directions. Like, limits cannot increase or decrease without bound, meaning if you're following your curve and it's going up to positive infinity or down to negative infinity or both if the limits aren't agreeing, then you don't have a limit. The limit does not exist. All right, we'll talk about one-sided limits in a second. And the last is that it can't oscillate between values near the limit value. So if your function is starting to wiggle all over the place and never settle into a value, and the limit does not exist. All right, so there are some properties of limits, and we're kind of breeze over them because they're kind of obvious. But if this is the technical definition of them, if you have a limit for your f, and as your x goes to c, you're going to L. You know that the limit is L. And if you have another function, g, and at c, it's going to m, and you add those two functions together, you're really just doing, you can do each one individually and add them together, and you still get the same answer. So in other words, you can say this. So if you know each limit individually, you can actually just go, all right, do the limit of f, do the limit of g, and I put a c in there instead of an x, my apologies. Then you can just go ahead and say, well, that's going to be L plus m. Same thing with subtracting. I'm going to skip the writing out the each limit. You can just say that's L minus m. You can do the limit of f and you can do the limit of g and just subtract those two limits and you still get the same answer. Same thing with multiplying. All right? And same thing with dividing, provided that your m is not 0. Okay? If your m is 0, all bets are off because you can't divide by 0. Same thing if you have a number out in front. If you have a scalar, this has to be an actual number, not like a variable. But if it's a number, all right, then you can just say, well, that's k times what you had for the limit for f in the first place, so k times L. And the same thing works for power. You can do your limit that you knew f was and raise it to that power, and you'll still get the same answer for the limit. All right, so that probably is looking a little weird, so let's actually do it in a problem. So the following limits. We're going to actually skip the first one and do the second one because it's a little more intuitive. So if I'm finding the limit of x to the third plus 4x squared minus 3 as x goes to 3, well, if you're graphing that, there's an actual point at x equals 3. So how do I find the value? Well, I put the 3 in. Well, for this x to the third part, that's 3 to the third. For this other part, for 4x squared, you put in the 3, and you get 3 squared. And you can add these values together. And the limit as x goes to 3 of negative 3 is just minus 3. And so you can find each of those values and then add them all together, and you get your limit because you get your value. All right, so if you do that, you end up with 60, okay, which happens to also be the value of the actual function. Now, same thing down here. You can go ahead, if you can plug in the value, do it. So for this guy, I'm going to get 3 times 2 minus 3, 3 squared times 2 minus 3. So I end up with negative 9 when all is said and done. You try the last one. I think you can do it. Alright, I hope you paused. If you got 3, you are all good. Just plug it in. Now, the same thing's true up at the very top. I said we come back to it. If you're talking about the limit of that guy as you go to C, as x goes to C, well, you're just putting in C. Alright, that's all there is to it. It's as simple as that. Now, so the top here is just a repeat of the previous page. We got 3. Now, what happens on this next one? What if x is approaching negative 2? What the heck do we do? Because if you put it in, okay, on the top I have no problem. I get negative 2 squared. I get plus 2 times negative 2 plus 4. Okay, so I end up with 4, 8 minus 4. I get 4 on top, but on the bottom I have a problem. I'm dividing by 0. I cannot do it. And so we have to have some other techniques. So first, let's use our graphing calculator. For now, if we can't find the limit, let's use our graphing calculator. So stop and try it on your graphing calculator. All right, I hope you got a graph that looks sort of like this. This looks like there's an asymptote going on right about there at negative 2, which I hope so because we can't divide by it, so it's not in our domain. All right, so what's happening? As I come from the left, I'm going to negative infinity. As I come from the right, I'm going to positive infinity. So the limit does not exist. All right, we abbreviate that DNE, does not exist. All right, it does not exist. So you can't have limits not agree. It's going to one negative infinity from the left and positive infinity from the right. They're going to infinity. They're increasing or decreasing without bound. So no limit. Now, what about something like this? It also divides by 0, but just because it divides by 0 doesn't mean that you can't do it. So we're going to look at our graphing calculator first. Okay, you should have gotten a graph sort of like this. Okay, and we're looking for the limit as x goes to 0. So what is the value there? Now, there isn't an actual point there. It should be open circle because we can't divide by 0, so there's no value there. But if we approach it, what value do we get close to? If you look at your graph, and on your graphing calculator, it's about 1. I'm thinking it's 1. We're going to talk about how to look at that possibly as an algebraic problem as well. So I need you to think about tangent as being, I'm going to copy down my limit part, as being sine over cosine. If I do that, I really have this as what I'm asking for. So sine over cosine and then all over x. I'm going to multiply by 1 over x so that it doesn't look so crazy. All right, so I'm going to rearrange that a little bit. So really that's sine over x times 1 over cosine over x. and we're still talking about as x goes to 0. But our product rule said that if I could find each individual limit, I'd be good. So I can find this limit right here. If I do 1 over cosine, that's 1 over 1. Because 1 over cosine of 0 is 1 over 1. So that part is just 1. All right? So how I did that is 1 over cosine of 0. By the way, if you're not getting your graph, it's because you didn't switch your calculator to radians. Okay? So you get 1 over 1. So that's how I got this value right there. Now this guy is a little trickier. All right? I still am dividing by 0, so that one we're going to have to go to our calculator, and actually we're going to go use some other proofs later on and not talk about it. AP, we'll talk more about it. Regular level, your calculator's good enough. If you look at your calculator, that also is 1. So you have your limit as x goes to 0 is 1 times 1, so you should get 1. All right. Now, how about this bottom one? Also, it's going to 0 if I put in x equals 2. I can't just substitute it in and get a value. So the bottom is going to 0. I can't divide by 0. I can't get a value. For right now, we're going to look at the graph, and it should look like something like this. There's an asymptote at that 2. So what's happening? We're going up without bound, or down without bound from the left, and from the right, on the right-hand side of 2, we're going up without bound. This limit does not exist. DNE does not exist. All right. So you can have limits that differ from the left and the right. So let's talk about left and right-hand limits a little bit. All right, so I'm talking about this function that's absolute value of x over x. So what does that look like? I'm going to define it piecewise because it's a little bit easier to look at. So if I'm talking about where x is bigger than 0, so all positive numbers, when I do the absolute value for this top part, the numerator rather, it's always going to be a positive number. On the bottom, I'm always going to have a positive number that's the same value. So I'm going to have just plain old x divided by just plain old x. I'm going to have 1. Positive 1 all the time. Positive divided by a positive, always positive. Now, on the other hand, if I'm talking negative numbers, x is less than 0. My top number is always going to end up being positive because it's an absolute value. So my numerator is going to be positive because absolute value, positive, negative, it's going to be positive. But the bottom is going to be negative. So if I have positive x divided by a negative x, I'm going to get a negative 1. So that part is always going to be negative 1. You can graph it on your calculator if you don't believe me, and I'm going to actually make my 1 marks be a little bit spread out so I can see it. But we're going to get this looking like this. Now, both are open circles because I can never divide by 0. I have no value at x equals 0 because if I put it in, it doesn't work. I cannot divide by 0. So both parts are open circles, open points at both endpoints of those rays. Now, if I look at this, the limit as I go to 0 does not exist because the limits do not agree. As I'm coming to 0 from the left, I'm going to 1. I almost said 4 because I didn't write down my little scale. I made it stretch out, so those are going to 1. My value is 1. And then I said 1, it should be negative 1. All right, so from my left, I'm going along and I get closer and closer to negative 1, but coming from the right, I get closer and closer to positive 1. So those are something we call left-handed and right-handed limits. And you put this little negative sign that lets you know that you're coming right there. See it? That little teeny guy? You put x approaches 0 from the left. That's what that means. If you put a little negative sign, it's almost like where you put the exponent, and it means that I'm approaching 0, but only look at it as if you're going along the curve up to it from the left-hand side. Don't care about the right-hand side. This little plus sign means I only care about if I'm traveling closer and closer to 1 coming from closer and closer to 0 coming from the right. So as I come from the right, I'm getting closer and closer to 1. Actually, I'm 1 consistently all the time. And same thing, if I'm coming from the left, I'm consistently -1 all the time. So my limits differ. From one direction, it's -1, and from the other direction, it's +1. I can talk about my left-hand limit, and I can talk about my right-hand limit. They don't agree, so the limit overall does not exist. So in other words, the limit as x goes to 0 up here at the top does not exist. Why? Because my limits do not agree from both directions. It is helpful sometimes to talk about the left-hand limit so we know what it is from the left, and it's useful to talk about the right-hand limit so that we know what it is from the right, so we kind of know what its behavior, the behavior of the function is. But the overall put together, the limit at 0 does not exist because it's not meeting. They're not meeting in the middle. They're not meeting at the same place. All right, so I've got this little graph here, and I want to talk about the left-hand limits, the right-hand limits, and the limits overall. So if I'm talking about this graph that I drew out on your left-hand side of your notes and your screen, and I'm talking about the limit as x goes to -7 from the right. That's what that little plus sign after the number means. So -7 is right here, okay? And I'm talking as it comes from the right. So here's -7. So what's to the right of it? Stuff over here, okay? So I'm coming from the right, meaning I have to follow the curve from the right. What is it approaching as I come from the right and I end up at -7? Well, it looks like it's approaching right at 5. Let me make sure I counted right. 1, 2, 3, 4, 5. So I'm getting up to 5. 5. That's my limit from the right. Now, what if I'm talking about from the left? Well, that means here's -7. This side is the left of -7, so I have to come along the curve going up to it, going up to -7 from the left. Well, when I get to -7 on the left branch of that function curve, to the left of -7, I end up at 2. Okay, when I hit -7 coming from the left, I end up at 2. Okay, so I end up at 2. Now, that is not my value. One of those is my value of the function there, and that happens to be 5. Excuse me. So we're going to come back to that in a second. But what's the limit overall as I approach -7? Well, it does not exist because my two limits are totally different. Since my left-hand limit is one thing and my right-hand limit is a different thing, I get 2 and I get 5. If it's not meeting, basically they have to be coming together at a point for that to happen. The limit does not exist because they are not coming together, they are not meeting, they are not the same limit from the left and the right. So overall, the limit does not exist, but it is useful to know what we approach from the left and what we approach from the right. Now, that said, that is very different from the value of the function. Up above here, the value of the function at -7 is actually what the plotted point is. Well, the plotted point is f of -7, where it's filled in, is actually equal to +2. Up here at 5, it's an open circle. There's actually no value of the function there. The value of the function is right there. All right, so if I'm going to add this to this same graph. Consider -4 instead. If I'm talking about the limit as x goes to -4 from the right, that's what the little plus sign means. And so I'm coming on this side of -4. I'm going toward -4 from the right. I end up at, like, we're going to say that I can actually draw my graph, and it's about 8. Now, if I come from the other direction, and I'm coming up to from the left, okay, that's what that little negative after the 4 means. Okay, so I'm going to -4 from the left. I also end up at 8. So in this case, the limit as x goes to -4 does exist. They agree from the left and the right, so the whole limit is 8. So if both the left-hand side and the right-hand side agree, then the whole limit is exactly what both of those left and rights are, and then they're the same, 8. It actually happens to be the value of the function. If there were an open circle at that point, that would not be the value of the function. So it happens to be that f of negative 4 is also 8, but it does not have to be that way. So I want you to practice doing this piecewise function yourself. So see if you can draw it, pause, see if you can draw it, and then compare with my answer when you unpause. Okay, so hopefully you paused and did that. Let's see, I got these two branches. First the parabola, less than 2, and this guy over here, bigger than 2. Now, there is a little break in my graph. It's discontinuous. So as I approach 2 from the right, so on the right-hand side of 2 is over here, so I'm coming down toward 2 from the right. I am getting closer and closer to 5. As I approach 2 from the left, so I'm on this side of 2, I'm coming closer and closer to 2 from the left. I end up at 4. Okay, so my limit overall does not exist because, again, they do not meet. They have to meet, they have to match from the left and the right for the limit overall to exist. So I want you to go ahead and look at this unbounded limit by looking at its graph at first. I'm going to pause and draw my graph in. You should do the same. Alright, so my graph looks like this when I graph it. There is an asymptote at 0 as well. I didn't draw in, so if you really need that to be there, there you go. Alright, so now the question is asking find the limit as x goes to negative 2. Alright, so we have to check both the right-hand and left-hand limits. So if I go from negative 2, approach negative 2 from the left, that's what the negative after it means. So I'm coming from the left of negative 2 over here on this side of negative 2, coming on close, I'm going up to positive infinity. Alright, so my limit is going to positive infinity, but that means it does not exist. Now, I like to see that it's going up to positive infinity, and that's why it does not exist. It's an explanation. You can't say it equals positive infinity. That's not a number. You can say it equals positive infinity and then says does not exist. It's really important. The limit does not exist if it's going to positive or negative infinity. Now look at from the right, it is also going way up to positive infinity. If I'm approaching negative 2 from the right, all right, that's what the plus sign means afterwards, I'm also going up to positive infinity. Now, the left and the rights match, but again, the limit does not exist when we go to infinity. So overall, the limit does not exist because overall, yes, in general, it is going to positive infinity in both directions. The limits match, but we're going unbounded to infinity or negative infinity. If that happens, that also works. The limit does not exist. All right, so I wanted to show you a really kind of funky example. I want to find the limit as x goes to 0 of 1 over sine of 1 over x. It's really important that you're in radians. So I want to graph it on my graphing calculator, and I got something that ended up looking very close to this. It did something funky in here, but it wiggled around, but it pretty much looks like it's going to 0 here in the center. So I'm looking like it looks like it goes to 0. Now, when I graphed it on my TA84, it looks a little different than I've graphed it before, but it looks like it's still kind of going toward there, but still doing kind of funky things in the middle. So I want you to zoom in. Don't forget to push enter and see what it looks like. Well, if you look at the middle now, after you do that, it looks like it's got some funky stuff going on. Alright, so you're going to try several strategies when you're trying to do limits. First things first, you want to substitute directly. If you can substitute the number in and get you a value out, that is the easiest thing to do. Great, do that. Next, after that doesn't work, you might want to do some algebra. So the third thing you're going to want to do is try to rationalize. So if you have a square root or a cube root or some other kind of root, rationalize. So in this example, for instance, I put in my 2 on my bottom, and I get 2 squared, 4 minus 4 is 0. I can't do that, okay? I end up with something 0 divided by 0 at that, so I cannot do that. All right, so I cannot directly substitute, so I got to try something else. Algebra. All right, so the top I can't do anything with, but that bottom is a difference of squares. If I factor that, so that's something you should just recognize. That's how you factor it. And then it factors. Now, it looks like these kind of cancel, but they don't exactly cancel. I see that one is the opposite of the other, so I'm going to do a little trick here. I'm going to factor out a negative on the top because I see that then I have negative 2 plus x. All right? I'm factoring it out because then these really are the same, this on the top and this on the bottom. I can cancel them. If I put the x plus negative 2, I think you can see that those are the same. So really, if I keep reducing this, I have got, oopsie, sorry about that. I have got limit as x approaches 2 of negative 1, because you have to have something on top, over x plus 2. Now I can put 2 in. So now I'm to a point where I can actually just stick in 2. I get 2 plus 2. I get negative 1/4. That's my limit. So I've used some algebra to simplify the problem a little bit to make substitution possible. All right, so look at this next one. Now I can put negative 3 in that one. So go ahead and substitute it in. Negative 3 squared minus 3 minus 6, or plus negative 3 minus 6, and negative 3 minus 3. I get 0 over negative 6, so just 0. So this next one, however, I can't put in 1, because if I try to put in 1 on the bottom of this guy, I get 0 over 0, which I can't divide by 0, so I can't just substitute. So I need to try some algebra. Let's factor. Okay, so factoring that one, you have to remember just difference of cubes. If you look at, I believe it was the green sheet I gave you, that with the algebra on top, it will give you the formula for that. I did put it over here on the side for you. All right, so what do we get when we get ours? So we would have x minus 1 then, and then 1 squared, or 1 plus, x squared plus 1x, and then plus 1 at the end, because negative 1 times negative 1. All right, so there you go. And we have that over x minus 1. Now, these terms can cancel since we're talking two factors. Okay, we had two multiplied things. We can factor those and cancel them. Now, I can plug in 1 to this because I don't have any division, so I don't have any problems. So I can substitute 1 in, no problem. 3. Done. All right, so what about with these darn square roots? Some fun stuff happens when you do this. Now, I can't plug in or substitute in 0 because I would divide by 0. There's no real factoring you can do, but you can rationalize. And one way to do that is, we don't have to rationalize the denominator, although if it's in the denominator, you do that. There's a trick. Multiply by the conjugate. If you remember what conjugate means, it's instead of 1 minus 1, x plus 1 minus 1, you multiply by plus 1, and it makes a very nice thing happen when you FOIL, when you multiply out. So square root times the square root is going to just be x plus 1, because the square roots are going to cancel. Square root squared just cancels. Okay, plus 1 times the square root of x plus 1 minus 1 times the square root of x plus 1. Those middle terms will cancel, minus 1. And that always happens. This middle term always cancels because positive 1 square root of x plus 1 minus 1 square root of x plus 1, they cancel. And that will always happen, and that's why you multiply by the conjugate. So our top actually ends up looking a lot less crazy. Now our bottom, on the other hand, looks worse than ever, but we don't care as long as our bottom ends up being nicer when we factor and cancel. All right, so my top right now, since I cancel these guys out, I subtracted them and they eliminate each other. I have x plus 1 minus 1. well, what's x plus 1 minus 1? Well, it's just x. All right, so I have x on the top. I have x on the bottom times that crazy looking stuff. And you're like, why, Miss Kite, did we do that crazy looking stuff? It's still that crazy looking stuff. I forgot to write my 0 up here because now those x's do cancel out on the top and the bottom. So now when so there's a 1 up here. Okay, the coefficient in front of x is 1, so that 1 is still there. All right, so now if I go ahead and substitute in 0, even though it's a crazy looking thing at the bottom, I can do it. So 1 over square root of 0 plus 1 plus 1. Well, I can do the square root of 0 plus 1. That's 1. All right, so on the top I get 1. And on the bottom, if you do that math, it's 2. The limit is a half. All right, so let's do the same trick on this other one. We're going to multiply by the conjugate. So I have a minus there, so I'm going to multiply by the same crazy looking thing, but with a plus. It's called the conjugate. But I can't do it on the top without doing it on the bottom, or I'm changing my problem. Now, when I FOIL, I get 2 plus x plus the square root of 2 times square root of 2 plus x minus the square root of 2 times square root of 2 plus x, okay, because of this, and then that, and then minus square root of 2 times square root of 2, which would be 2, all right, all over x times the square root of 2 plus x plus square root of 2. It looks icky on the bottom, but we had to make the bottom look icky to get rid of some of the top. So these guys are opposites of each other, positive and negative. They're going to subtract from each other. And I now have 2 and minus 2, so those are going to cancel. So I only have x on the top and an x on the bottom. So I'm going to rewrite that because it's starting to look a lot crazy. Starting, Miss Kite, starting. It is a lot crazy looking. All right. Now, so this is what I have once I've canceled out on my top, my like terms that ended up eliminating from each other. So now I've got an x factor on the top and an x factor on the bottom. I like to write that leading coefficient of 1 in there just in case, because when I cancel those two guys out, a lot of people like to go, well, what happened to my top? Well, it's the leading coefficient of 1 is there. You just don't usually write it in front of the x. Well, it's still there, even though you didn't write it. All right, so now when I plug in my 0, substitute in my 0, I should get 1 over square root of 2 plus 0 plus square root of 2, which equals 1 over 2 root 2. And if you want to do that as a calculator problem and get a decimal, I'm all over that. You do not need to change that so that there is no square roots in the denominator. It is acceptable for AP. It's acceptable for Miss Kite for you to leave radicals in the denominator as long as they're reduced. You should not leave like the square root of 4 because you can actually do that. You should not leave the square root of 18 because you can reduce it to 3 root 2 and so on. But you can leave them in the denominator. All right. This last one is oh so fun. So we're going to try to combine fractions in order to do an example like this. So I can't put in 0. Always try that first because sometimes they look crazy, and if you put in the number, they're not so bad. But I can't divide by 0. I'm going to end up dividing by 0 right down here, and that's a problem. So I'm going to try some math. All right, my first instinct is to go ahead and make these fractions on top be combined. All right, so the limit as x goes to 0, and I'm going to combine the fractions on top. If I want to combine the fractions on top, add them, I need to have a common denominator. So this guy is going to get multiplied by 4 over 4, so I'm going to do that there. And this second one, I need to multiply by x plus 4 and x plus 4. All right, and I still have the whole thing over x. So now, my top. It is really important that you write the limit every time. I am very good at forgetting it, I have to admit, but please do that. you have to distribute this negative, okay, to the parentheses. So it's like a -1 that's the leading coefficient right here because of that minus sign out here. So I'm going to do minus x minus 4, which you can see is making our top of that look very nice. And I have 4 times x plus 4. And that whole thing is over x. All right, well, the 4 and the minus 4, they eliminate from each other. All right, I usually do this step early on because I really don't like that fraction inside a fraction. It drives me crazy, but I continue doing it. If you like doing it earlier on, fine, but dividing by x, okay, I like to think of as multiplying by 1 over x because multiplying by the reciprocal, and it makes your life easier. I actually would have eliminated it up here and written it out here because that's the way I just don't like looking at it. I do it right away so that I don't have so many fractions inside of fractions. I hate that. It drives me crazy. It's not wrong. It's too much for me. Now, the leading coefficient, remember, in front of this guy is -1. But we have an x on the bottom, which it's multiplied, so it's a factor, and we have an x on top, so we can cancel them. So I'm going to cancel those because x divided by x is 1. So I'm going to go ahead and say now I can put 0 in the bottom. I'm not dividing by 0. I got rid of that x. So I have -1 on top, and on the bottom I'm going to have 4 times 0 plus 4. I'm going to end up with -1/16. There we go. So as long as you can remember some of your algebra skills, it's not always fun, but we got some factoring involved, some rationalizing radicals involved. We've got some eliminating like terms from the top and the bottom, both adding and division, and we've got some fun adding fractions. Lovely. Now, the sandwich theorem is really very basic. I don't want to go over it a lot. It's sometimes covered on the AP exam, so this is definitely, we're going to cover it very briefly. So here's what it basically says. If you've got some functions and you don't know a whole lot about f of x, but you know that it's always between g and h, okay, and you're trying to find the limit as x goes to c for f. All right, but you don't, it's really hard to tell what it is because it's a crazy function. But you can tell what g and h go at c, and it just so happens that they end up going to the same thing at c. They have the same limit. Well, if f is always between g and h, and they go to L, well then f goes to L. So what I mean is this. If you graph this guy, all right, you will see that it looks like this. And I actually also drew in x squared and the opposite of x squared. So my graphs, I did not use the scale of 1 by 1, just so we all know. But I know that this is always between them. Just looking at my graph for right now, that's good enough. So the sandwich theorem, also known as the squeeze theorem, says that if I have got this one squeezing it in and this one squeezing it in, and I know that these both are coming to 0 at 0, so this guy that's always in between them, well, it's also got to go to 0. So that's all the squeeze theorem says. It's saying that if you can sandwich it between two things or squeeze it between two things, and those two things come to the same limit, say at 0 right there where they're both coming to a point, then the other one has to too. That's all it says. The one that's in between, it's also going to stay in between at the limit, and so since they're the same, it's also the same.